Hello 317 students, I hope you're all healthy and sane. In this video, I'll explain our plan for adapting the course for remote online instruction and then provide a tutorial on some new tools that we've developed to replace the use of the laboratory equipment in class. The new syllabus is posted on Moodle Dropbox. I've updated section 2 to indicate that we'll no longer be meeting as a class. I'll be uploading the lectures on YouTube as I have in the past. You'll be working on the projects from home. There's two options here for how this will work. You'll either remotely access the lab computers from home, or you'll have to install Linux locally on your home machine. Remotely accessing the lab is the simpler option. Installing Linux locally is a bit more complex. However, Charles has recorded a nice tutorial on how to do that, which I'll include at the end of this video. I will cover how to do the remote access. If you need help getting set up to work from home, please don't hesitate to contact us through email, and our email addresses are shown there. Okay, so to access the labs remotely from home, if you're using Windows, there's two pieces of software you have to download and set up. The first is the Cisco VPN client, and the second is an SSH plus X Windows client. So to do that, you can get the VPN client from my.sc.edu/software. Log in, and under security, click Cisco AnyConnect VPN. Click the checkmark box and continue. Go to downloads, log in again. You may have to authenticate through Duo, and then click on Cisco AnyConnect VPN and the green download button. Download that. It's downloaded as a zip file. Once it's downloaded, right-click, extract all, hit next, double-click on setup, click OK. Deselect all these options. Just turn on Core and VPN. Click Install Selected. Once that's installed, you can access Cisco from Cortana or the Start menu. Just type in Cisco. Click on Cisco AnyConnect Secure Mobility. Click Connect. Type in your university credentials. Click through on Duo. And you're in. When you're ready to disconnect, you can access the Cisco icon from the system tray and click Disconnect. Now that we're on the VPN, you can download the secondary program, MOBA Xterm. So search for MOBA Xterm on Google. Click the download link, click download for the home edition, and then you can click this portable edition link or button. It's also a zip file, so save that. Once that's downloaded, right click the MOBA Xterm icon, extract all, and then double click on MOBA Xterm. Now it may prompt you for a password for your master keyring. That's because MOBA Xterm by default will save your SSH password. So if you get that, just put a password in and commit that. Okay, once you're into MobaXterm, you can start local terminal, and to connect to the lab machines, you would just type SSH-P for port 222, and then your username at L-3D22-01.csce.sc.edu. Now, once you connect, you're actually going to get two duo authentications. The first would be for the file browser that's on the left-hand side of the window here, and the second is for the actual terminal. So I'm going to respond to Duo. It's already come up on my phone once. Okay, now over in the terminal, I'll tell it to authenticate a second time. Then I'll get another Duo ping, and now I'm in. So on the left side, I've got the ability to browse my files, and on the right side, I've got a terminal. In order to test out graphical, the graphics, the X server, you can type XEyes, which is a little test program, brings up an pair of eyeballs to test whether your graphical connection is working. And if you see those, and you can close that, you know it's working. So that's it for Windows. Now, for if you're on macOS or Linux, you would still have to download and install the Cisco AnyConnect VPN from the same spot. They have macOS and Linux versions of it. For macOS, you would have to download and install Xquartz from xquartz.org, which is the official macOS X Windows server. Linux, you wouldn't need to do that. And then, in order to connect to the lab, you would connect to the VPN, and then just as we did in Windows, and then you'd open a terminal and type in SSH-P222. You'd also have to add a $Y for it to tunnel the graphical connections back through the X server. The SSH connection rather, and then username at L-3D22-01.csc.sc.edu. You can replace the 01 with any number between 0, 1, and 20 in order to choose different machines in the lab. Okay, so back to the syllabus. We've updated the grading structure. Lab 1 will still count, and the grades for that are up on Moodle Dropbox. Lab 2 will unfortunately have to be dropped because we never finished that. We will add 3 new individual labs, so we will be disbanding the groups from here on out. So you will work alone and develop these programs, these programming-based assignments alone, and you'll be graded on them individually. We will still administer Moodle-based quizzes, and we plan to administer the final exam on Moodle as well. So moving forward, the first programming project will be concerned with SPI because that was the objective of Lab 2, which we're replacing. I've covered SPI in the last 2 lectures, but it's been quite a while. It's been 3 weeks since the last lecture, so I'll briefly review that. SPI is a serial connection between 2 components. It sends 1 bit of data at a time. One side of the connection is the master connection, which is typically the CPU, and it's the entity that initiates the transaction. There's a slave, which is typically the peripheral, which is a sensor, actuator, storage device, memory, display, or any other kind of I/O device. It must respond to the master's initiation of transactions. An SPI transaction is an exchange of 1 or more bytes. So the master and slave will always exchange a number of bytes that comprises the transaction. All right. So if it's a 2-byte transaction, the master will send 2 bytes to the slave, and the slave will always send 2 bytes back to the master. When you're doing a read or a write style operation over SPI, meaning that you're using SPI, which exchanges bytes fundamentally, but you're using it to read an address or write an address on behalf of the master to the slave. Often this will result in some of the bytes being exchanged not being needed. For example, if the master wishes to read the contents of an address from the slave, then 2 bytes will be exchanged between the master and slave. In the first byte exchange, the master will be sending the address and the read flag, a bit indicating that it wants to read. The slave will be sending back a dummy byte, a byte that will be disregarded by the master. Then in the second exchange, the master will send a dummy byte, and the slave will send back to the master the contents of the address that it wished to read. On the other hand, if the master wishes to write a data to an address on the slave, then in the first exchange, the master will send the address and a write flag indicating that it wishes to write. The slave, as before, will be sending a dummy byte back to the master. And then in the second exchange, the master will be sending the data, the byte that it wishes to write, and the slave will be sending back a dummy byte. Okay, so going back to the previous slide, recall that SPI channels, when I say channel, I mean connection between a master and a slave. The channels consist of 4 wires, but the naming of these wires is not consistent, even within the materials that we distribute as part of the course. There's a but the purpose of the wires is consistent. It's just the naming that sometimes can get confusing. So there is the wire, the signal shown at the top of the timing diagram on this slide is labeled CS, which stands for chip select. In other places, it'll be SS, which is slave select. But it's the first signal that changes its value during a transaction, during an SPI transaction. So it will be high. It will always be high, logic 1, when the channel is idle, and it will go low during each series of SPI byte exchanges that make up the whole SPI transaction, right? So you see that signal at the top, goes low, and then the exchanges happen, and then it goes high. Right? Then there's the SPC signal, as shown on the slide, but that's also called SCL or S clock. It's the clock signal, and it's the signal that clocks the bits between the endpoints. So there's 1 clock cycle per bit that's transacted. It's the reason why this SPI is considered to be a synchronous bus, is because there's a clock that indicates each bit being transacted between the 2 endpoints. Now the clock may be either high or low when the channel is idle, depending on the setting of the CPOL, C-P-O-L. Right, so in this example shown on the slide, CPOL is 1, meaning that the clock is 1, is high, logic high, when there's no transaction going on, and then during the transaction it alternates between 1 and 0. Then there is the bottom 2 signals, which are indicated as SDI and SDO, which also sometimes are called MOSI and MISO, but this is the bits that are transacted. These are both used for the bidirectional flow of bits between the 2 endpoints. So there is, in this case, it's SDI stands for serial data in, and SDO is serial data out. Serial data in would be equivalent to MISO, which is master in, slave out. Serial data out would be master out, slave in, MOSI. So this is always a little confusing, because when you say in and out, the question is, are you referring to, what is in and out relative to, the master or the slave? If it's relative to the master, then SDI, serial data in, would be the master in, slave out, and the SDO would be the master out, slave in. So I prefer MISO and MOSI as compared to SDI and SDO. But basically those are the bit either flowing out of the master into the slave, or out of the slave and into the master. Okay, so I mentioned that CPOL is the clock polarity. It specifies the idle state of the clock, and for lab 2, that value is 1. Why did we choose 1? Well, that's because that's what the accelerometer that we had planned on using for lab 2 was assuming that setting for CPOL. So we will just go along with that. We're going to leave that as 1. And again, that means that the clock is high when the channel is idle. Then there's CFA, which stands for clock phase, and this one is a little bit more subtle. In lab 2, it was also 1, and what that means is that the data, and when I say data, I'm referring to both MISO and MOSI. The data is expected to change on the first edge of the clock, and it is supposed to be sampled on the second edge. Well, if CPOL is 1, that means the clock is normally high, means the first clock edge is a falling edge from high to low. So if CFA is 1, then the data is going to change on the first falling edge of the clock, right? And then it's to be sampled on the first rising edge. Now you might say, well, as opposed to what? I mean, what would be the alternative? It's, the alternative would be for the data to be sampled on the falling edge, which would imply that the data must have been set up before that, which meant that the data would have to be set up sometime before the first clock edge, right? To me, I think it makes more sense that that when you initiate a transaction, the chip select goes low, then the clock goes low, at which point you also set up the data. Master and slave establish their data, their bit. And then on the following rising edge of the clock, you will be sampling the data, which gives you a half clock cycle to get the data ready to stabilize the data on MISO and MOSI. Okay, so that's the setup we're using in lab 2. When we were using the 328P, we had 2 options for how to use SPI. The first was to drive 3 of the SPI pins, the outputs, which would be the chip select / slave select, the clock, and the MOSI, by wiring values. By writing values to the port outputs, treating them as GPIO, and then the input, which would be MISO, you would read those using the pin, right? So remember that there was port B, port C, port D. There was pin B, pin C, and pin D, which was how you would, from the software, you would directly write and read pins on the 328P. This is what we call bit banging, meaning that the operation of the SPI connection is controlled entirely by the software. In the example I showed in class where I did this, I also used the timer to control that process as well. I used a timer and a timer interrupts as opposed to just using busy waits in the software in order to synchronize the bits being written to SPI. But you don't have to use the timer. You could just use busy wait. In other words, the delay microsecond function. So that's what I'm showing at the top of the slide. So in this case, you've got from the master, you would have your code that would be writing to DDR, which is the data direction register, which defines which pins are inputs and which pins are outputs, port, and actually that should say port and pin, right? Because the port is for the outputs and the pin is for the inputs. And then optionally, the timer as well to control the timing. The second option was to use the hardware capabilities of the 328P to control the SPI channel, in which case the software only needed to control the slave select or the chip select pin. So you still needed to use the DDR and the port for that. Of course, you had to use the specific pin that was in that case you would have to use the specific pin that was set up for the slave select, which I believe was on the port D. But anyway, the software would still control the slave select, but the hardware would take care of sending the bits out of MOSI and reading the bits on MISO through the SPI data register SPDR, and then there was an SPI control register SPCR and an SPI status register SPSR that was used for additional configuration. So that's where you'd set up the speed of the channel, interrupt handler, that sort of stuff would be done through there. So basically, in that case, the hardware would do most of the work for you, and the software, you wouldn't have to worry about having to control everything in the SPI channel with the software. So those were two options, right? There was a software controlled SPI, which was also called bit banging, and then there's the hardware controlled SPI, which is where you're using the built-in SPI hardware in the chip. Okay, so now I'm going to talk about the changes that we're going to make to the labs in order for us to continue working on this without the boards. So in the new lab 2, we're going to use a new interface. You're going to be writing code that talks to an SPI channel, but through a new interface, which is very similar. It's designed to be similar to the bit-banged GPIO interface, but it's actually simpler. And it's simpler because instead of having to control the DDR register, set up the DDR, the data direction, and you have to bit twiddle in order to set bits to 1 or 0 in the port, or to extract specific bits out of the pin, right? And again, port and pin are the control registers on the 328. In this case, we're going to provide you a write IO function, which will allow you to read. The write IO is writing, so you're gonna be using that to set the slave select, the clock, and the MOSI, and then there'll be a read IO that allows you to read the MISO, right? And then you can initiate waits using the delay cycles function, which is kind of equivalent to sort of like the delay _ US, right, that we used before, except that was in microseconds as opposed to cycles. So from your code will just have to essentially use those 3 functions in order to generate a valid SPI transaction, right? So you're going to write code, and then by calling those functions in the proper order and in the proper way, you'll be able to send bytes or exchange bytes rather with a simulated slave. Now, how are we simulating the slave? The behavior of the SPI interface will be modeled using a hardware description language, which is it's actually the topic of CSCE 611. Most of you haven't taken that yet. But a hardware description language is a high-level language that you use to model the behavior of hardware. So basically, it's like you're simulating a digital logic circuit. And in fact, we got the hardware description language for this SPI slave from we got it from GitHub. Someone had sent, it's basically an open source HDL. The HDL language is called Verilog, so it is a Verilog description of an SPI slave. And so we're also using a tool called Verilator, which will convert a given Verilog description, circuit description, hardware design, basically. It will convert that to C. So we've got this SPI slave. It's a hardware circuit. It's being converted to C, allowing you to run it as software. And then you will be linking your code against that, meaning that you're going to be writing code that's going to be manipulating input and output signals of a hardware design that will be that's being simulated by virtue of having been converted to C and running in software. So if your signals that you send to that hardware description are adhering to the SPI protocol, then that circuit will recognize the language that you're speaking to it, essentially. And also, the Verilator conversion allows us to also generate a dump file, a trace file, also a VCD, value change dump, which basically will take it essentially saves the timing diagram, the sequence of signal state changes to a file, kind of like a waveform, like a simulation trace, a waveform, that we can validate and decode using yet another tool called SIG-ROC. SIG-ROC stands for signal grok, or it's like a merging of the words signal grok. So that will allow us a second way that we can validate the correctness of the SPI transactions that you generate. So the new Lab 2 has essentially the same objective as the original Lab 2, with the only difference being the way that your code will talk or interact or drive and read the 4 SPI signals. Instead of using the 328p style interface, which again could be either through the port, pin, and DDR registers, or using the hardware SPI interface. So instead of doing it one of those two ways, instead you will call R functions to interface with the SPI channel and cause it to read the whoami register and also to read a data register. So specifically, the challenges are to translate the SPI timing diagram into a sequence of C function calls, and to perform a read operations for the slave on top of these 4 signals of the SPI interface. And what I mean by on top of, I mean a read, as I mentioned earlier, a read operation is going to require an SPI transaction including 2 byte transactions over SPI. So you're doing a read by initiating an SPI transaction that's doing 2 byte exchanges between master and slave, and then you have to do that twice, one for to read the whoami register and another to read a data register. And this is the same thing you would have had to do to interface the 328p to the accelerometer, except you would have been doing it in a slightly different way. But either way, you're still having to deal with the SPI protocol. So the whoami register is at address 0f as it was on the accelerometer, and then you're going to read a data at address 10 in hex, which that's actually a made-up address that didn't exist on the original accelerometer. It's basically a virtual address. So, to perform a read operation over SPI, you're going to be following the timing diagram that's shown in this slide. So, again, you're doing two transactions. One transaction, but it's comprised of two exchanges. Right. So, if you look at the top signal there, the top trace is the chip select, and the chip select is high when the channel is idle. It drops when the channel is being used, and then it goes back high when the channel is no longer being used. And so, even though you're doing 2 byte transactions between the master and the slave, that's all being done as part of one SPI transaction. So the chip select is low during that entire time. So then you have below the chip select, you've got the clock, and so the clock should be going through 16 periods. Why 16? Because there's one clock cycle for each byte, and there's 2 byte exchanges, and each byte exchange would require 8 cycles. So there's going to be 16 cycles in total. SDI is the serial data in, and so that in this case is actually the in is relative in this case to the slave, because the SDI is being driven with the address that you're reading, which is 6 bits, 5 down to 0. But the most significant bit is the read-write flag, which is 1 for read, 0 for write. The second bit, bit 6, is the multiple single, which is 1 if you're doing a multiple byte transaction, or 0 if it's a single transaction. We're just going to be doing single bit transactions for this lab, and then followed by the 6 bits of the address. So that's obviously is coming out of the master, so that's going to be on the master out slave in MOSI. So SDI, when they say serial data in, that's in relative to the slave, and out relative to the master. And then SDO is out of the slave, so that's going to be the response from the slave. So that's going to be coming into the master on master in, slave out. So now you see the SDO is just flat during the transfer of the exchange of the first byte, the address byte, right? So that means that there's kind of a dummy byte coming back from the slave to the master during this first byte exchange. The second byte exchange, you see the data being sent from, the response from the slave being sent back to the master, but you still see the master, the master, it looks like there's still data being sent from the master during the second byte transaction, but in fact that would just be a dummy. So this diagram could have shown that SDI could have just been a flat line in the second transaction. Now this picture came directly from the data sheet for the accelerometer, so that was the way they chose to show it. But basically, to state that another way, the SDI really just has 8 bits. So there's 16 total cycles. There's 16 bit times. But the SDI is only valid during the first 8 bits, and is a dummy in the second 8 bits, and the SDO is a dummy in the first 8 bits and is valid in the second 8 bits. So that would represent one read operation, and then for lab 2 you're going to be doing 2 read operations. So now in order to provide more details about the software and how to use it, and then to also show you a simple demo, I will attach to the end of this video a video from Charles that will demonstrate the use of this software. And before that, there will be a demo of how to set up a virtual machine.
Hello everyone. In this video I'm going to show you how to set up a development environment in VirtualBox that will allow you to work on your 317 projects from your personal computer. We are also going to get the Linux labs set up so that you can use those over SSH through the university VPN as well. But I know a lot of people prefer to work locally, and I know some of you may have limited internet connections, so maybe this will be helpful to those of you that are doing that. So if you are going to use the university workstations remotely, you don't need to do anything in this tutorial video. I've also assumed that you've already got VirtualBox installed on your computer. It is available on Windows, Mac, and Linux. It's pretty easy to install, and there's instructions on VirtualBox's website. So I'm not going to cover how to do that. Now, first thing you're going to want to do is go to ubuntu.com, and we're going to hit download, and we're going to go to Ubuntu Desktop 18.04 LTS, and you are going to want to download that. Now, I've already got it downloaded, so I'm not going to download it again, but you'll need this ISO image. Now you're going to want to also open up VirtualBox, so I've got mine right here, and I'm going to say new, and I'm going to just call this virtual machine CSCE 317. We're going to say Ubuntu Linux 64-bit. I'm going to allocate 2 gigabytes of memory. You can probably get by with the 768 default. If you've got a lot of memory, it doesn't hurt to allocate some more though. We're also going to create a new virtual hard disk. And a VDI will be just fine, and dynamically sized is fine as well. I'm going to set it to 64 gigabytes. The dynamically sized means that it will only use space on your computer that it actually needs to store stuff for the VM. So if you only use 1 gigabyte of data in the VM, the hard disk image will only take up 1 gigabyte. So it doesn't hurt to set this higher than you need. So we're going to do that. And so now this is ready. Now just to increase performance in the VM a little bit, I'm going to go here into the processor section and just bump it to 2 cores. And under display, I'm going to give it 128 megs of video memory and turn on 3D acceleration. This will just help it run a little faster. Ubuntu's kind of heavy. So, all right, so now that we've got that set up, I'm going to hit start. And I'll pull this over here. So this is the simulated screen, and then in here we're going to want to pick our ISO image. It's saying there's no OS installed, so it wants us to choose something to boot from. So I'm just going to go into my downloads folder here, and we're going to pick this one. And I'm going to hit start. I'll make this a little bit bigger. Alright, now I'm just going to click in here, and this is going to capture my mouse. So if you do this, you can press the right control key on your keyboard to release your mouse, or I think on Mac it's different, but it should tell you what it is in this pop-up window. I'm going to press enter for English, and we're going to say install Ubuntu. It takes a little while for it to boot up here. These. Once it boots up, it does have a mouse pointer integration, so I can do this and I won't have to press control to release the mouse. So that's convenient. I'm going to make this a little bit bigger still. There we go. I assume we're going to want English as our language. If you speak a different language, you could pick that, but I'm going to do English. And leave the keyboard layout as the default as well. Of course, if you use a different keyboard layout, you should pick that instead. And we're going to just say minimal installation, because we don't need Office software and games and media players. So we're going to do that, and then I'm going to say erase disk and install Ubuntu, and we're going to hit install. And it's going to say, do you want to create this partition? And we're going to say yes, because there's only one disk and it's the one that we created for this. I'm in the Eastern time, so I'm going to pick that time zone, but if you're in a different one, you can click around and pick different ones. I'm just going to call my user CSCE 317 user, and I'm going to call the computer CSCE 317 VirtualBox is fine, and then for my username, I'm just going to say user, and for my password, I'm going to just make it be password. super secure stuff. I actually want to call that CSCE 316. Cool. And I'm going to say log in automatically as well. This is just a VM. We're not connecting it to the, it's not going to run a public-facing server or anything, so security isn't really a concern here. So this way we don't have to actually log in through the login screen every time it boots up. So now it's going to keep on thinking. Should also have some kind of network connection, yeah. So that's good. You'll have that usually by default unless you've configured it otherwise. And if you don't like the default Ubuntu, you can also should be able to use something like Xubuntu or Lubuntu or something like that if GNOME isn't your thing. I'm just trying to stick close to kind of the defaults and what you've maybe used in the CSCE Linux labs and stuff. So if you're maybe not a Linux user, don't want to overwhelm you with a bunch of Linux stuff that's not really relevant to this course. If I knew how to do video editing, I'd do a jump cut here and edit this part out, because it takes a little while, but for those watching at home, you can probably just skip forward a little bit. I enjoy that we installed a whole bunch of packages that we didn't need, and now we're uninstalling them. That's good design on the Ubuntu people's part. Alright, so now that it's done installing, we're going to hit Restart Now. And we're going to hit Enter. It should automatically eject our boot disk. And if you're starting this up cold, like it's been shut down and you're just logging in, you can always go on here, and instead of saying show, it'll say start, and that'll launch it from scratch. Okay, cool. So now we're logged in. Yeah, we'll do a first time setup. We don't care about this. I don't want to send stuff right now. Cool. Neat. Alright, So here we go. We've got our Ubuntu desktop. We've got Firefox. I don't know. Probably don't want to use Firefox in VM because that's going to be super slow and crappy, but it's there. Yes, I'm sure I want to close. And you can go up here and type in terminal, and that's what we want. So there's our terminal. We should have it. So in the next video, I'm going to show you guys how to install all of the software that you need. This is just how to install Ubuntu in your virtual machine, because I know maybe some people will already know how to do that, and for those people, then maybe you can save some time by not watching this video. So cool. So I will see you all in the next. Hello everybody, welcome to the second video. In this video I'm going to show you how to take your virtual machine you created previously and get all the tools and dependencies and stuff you'll need to work on the CSCE 317 projects. And yeah, so I assume you've already followed that video. So I've got VirtualBox right here. I've got my machine over here and hit start. I've already gone ahead and installed all of the dependencies, so it'll be a little faster when I show it to you, but I'll still walk through the process to do that as well. There we go. So you're going to go up to Activities and open a terminal. And what we're going to do is do sudo apt-get install verilator gtkWave sigrock CLI and build essential. So I'll leave that up for a second so you can copy it down or whatever. And I'll go ahead and run this. And of course this is all already installed. When you run this for the first time, it'll probably say something like, are you sure you want to continue, yes or no, and you'll have to type Y and press enter and all that good stuff. So yeah, so we should have all that installed now. I'm also going to go ahead and install Visual Studio Code as well. Now this is installed through the Ubuntu App Store, since I believe it's distributed as a snap and not as a aptitude package. There's probably a way to do this from the CLI, but I want to do this. Well, let's see. Visual. There we go. Visual Studio Code. And we'll say install. And presumably it's thinking. It says it's already installed. Ah, there we go. So now if I go here, there it is. Cool. Now, I'm going to do another video to walk you through more of how to actually use all of the tools and stuff. But I do want to just show you how to make sure that everything's set up. So I've got this CSCE 317 folder, and I've already copied the files that you'll get for this lab in here. So if you don't have a shared folder set up, VirtualBox does have the ability to do that. That may be a good way to move files back and forth. The way that I got this on here is I just SSH'd into my laptop from this machine and copied it over through SCP. You could also probably install like Dropbox or Google Drive or something and use that to get at it through the web browser. There's a lot of ways you could get code to or from your VM, so I'll kind of leave that up to you guys. But anyway, I have it here, so we've got all these files. There might be, I think I still haven't written a README yet, so you'll probably have one of those when you actually do the lab, and stuff might change a tiny bit, but should be pretty much about the same. And so I'm just going to say make waves, which don't worry too much about what this is actually doing, because I'll talk about that more in the next video. So you should see this GTK-Wave window pop up, and it should have a little clock going along there, and some other stuff that's just kind of some straight lines and such. Nothing super exciting going on, but that's just fine. So that means everything's working, right? That means we were able to get Verilator to run, and GTK Waves is installed. We can also do a make decode, and of course nothing's been transmitted, so it's not actually decoding anything, but it also hasn't printed out any errors. So that's how we know that sigrock has been installed, and you know, if it says, you know, couldn't find sigrock or crashes or something like that, then you know, maybe you didn't install everything quite right. Okay, so in the next video we'll talk more about how to actually do the lab, but so this one was pretty short, but hopefully now you've got your VM set up and you've got all your packages installed to be able to work on the labs and everything. Hello everybody and welcome. In this video I'm going to be talking about how you can actually go about doing the labs for CSCE 317 now that we're doing everything all online. So the previous two videos were about how to set everything up to work locally, but everything in this video will apply whether you're working locally or on the University Linux labs. I'm going to be working through the setup I made in the previous two videos, so if you want to follow along exactly, you might want to check that out. Hang on, lost my... There it is. So I've still got the virtual machine running. I've got this folder here, which has got everything that will be in the lab skeleton when I pass it out to all y'all. I'm also going to go ahead and open up Visual Studio Code as well. Takes a little slow, but all right, and we're going to say open folder, and let's see, where did I put it? Here it is. So we're going to open up this folder. Hopefully this is all pretty familiar and not new, because this has not changed. So basically the way that we're reworking the labs for this, kind of the rest of this semester so that we can do everything virtualized is that we're going to shift less on reading data sheets and running on real hardware, of course, because that would be kind of hard to do in an online environment. So instead we're going to focus more on the actual signals and stuff themselves. So for kind of most of what you'll be doing is just directly implementing basically bit-banged quote-unquote versions of SPI and I2C. You did something like that for UART for the final component of the first lab, so it'll be kind of similar to that, although I think it's a little bit easier since you've got much better debugging tools and there's no resource limits or anything like that, so it's a little easier. The way that we're accomplishing that is we've got these Verilog files. You don't need to read these or look in them or anything if you don't want to. We assume that most of you probably won't know Verilog. So for those that aren't familiar, this is basically, it's a language that allows you to describe how basically a digital logic circuit or a chip, as you might say, works. And so we'll basically create a model of a simulated device that you're going to interface with, and then we're running that through a tool called Verilator, which will allow you to interface C code that you're going to write to the Verilog simulation. So for kind of the first kind of Hello World lab, you'll just be doing a basic bit-banged SPI with just a single slave device, and that's the sensor, which lives in sensor.sv for maybe those that have taken 611 or 313. Maybe this will be a little familiar. So you can actually kind of go in and see exactly how kind of the peripheral that you're interfacing with is working internally if you want to, and if you read Verilog. You normally don't have the luxury of doing that in the real world since you'll just buy a chip and you get a data sheet and you can't necessarily see what's going on inside. But I'm not going to harp too much on how the Verilog stuff works because that's not really part of this class, and we're not really expecting you guys to interact with that in any way. Kind of the main thing we've got going on here is this make file, which is a little bit different than the one that you've been using for the ADR, and it's got a couple of important components here. So the first thing is that there's a target called simulation, which actually produces the binary file that gets executed to run your code in the simulated environment. And so what that does is it takes in this vtop_all.a file here, which this gets generated by Verilator down here, and then it also takes in your code, which is this main.cpp. And then there's also a support.cpp, and that's some code that I've written that will kind of help give you guys an API and a programming environment that's a little bit more familiar to what you've been using in this course so far, so that you don't have to directly interact with the Verilator API. I guess technically you could if you wanted to, but we're not really expecting you guys to learn how to directly use Verilator on its own, because this is really about this is a hardware-software interfacing course, so kind of using those kinds of tools would maybe fit more in like a 611 or something. So again, don't worry too much if you don't quite follow what's happening with Verilator and whatnot. Another thing you'll notice is there's this trace.vcd. So a VCD file stands for value change dump. So it basically lets you record several signals and how they change with respect to time. So when you run your simulation, it's going to produce a trace.vcd. And so you can type make trace.vcd and it'll generate that for you if you want. You probably won't directly do that a whole lot though, because you'll probably mostly be using either the decode or waves targets, and these are basically shortcuts. So one of them, the decode, will take your VCD and it'll use SIGROC, which is a protocol decoder or a protocol analyzer, and it will basically look at what's in your VCD and print out what data it sees on the SPI bus. So it'll show basically first what transmitted from master to slave, and then what transmitted from the slave back to the master, and it just dumps that out, standard out. And then there's also waves, which will just open GTK waves, which is a program for viewing VCD files, and it'll run that on your VCD. If you have another program that you like to use to look at VCD files for some reason, then you can use that too, but this is what we're using. You'll also may notice there's this filter.vcd. SIGROC doesn't like working with VCDs that have nested scopes and stuff in them, so I've got a little script that pulls those out. You don't need to worry too much about how that works. Cool. So you may want to take a look at this support.h file. So this is you shouldn't change anything in here. You shouldn't need to change anything in here. But this will basically be the API you're going to use to interact with the simulated environment. So you've kind of got basically 4 kind of IOs or input outputs. You can think of them very much like the GPIO pins on the AVR. And I've called them SCK, CS, MISO, and MOSI, which are you hopefully recognize as the 4 signals that you've got for SPI. And I've got some helpers here. And so that's kind of all hard-coded in here. But basically, you've got these functions here. So you can say, for example, write to an I/O, and you'll give it one of these simulation I/Os, and that'll basically be one of I/O SCK, I/O CS, I/O MISO, or I/O MOSI, and then what you want to write it to, which will be 1 or 0. There's a read I/O, which is kind of the opposite of that, reads instead of writes. And then there's also a delay cycles, delay US, and delay MS. Now, kind of the delay US and delay MS are kind of smoke and mirrors in that they'll probably run a lot faster than real time. If you say delay for a second, it'll probably be quite a bit faster than that, because this is microseconds and milliseconds in the simulation time, not in. Oops, didn't want to do that. In the simulation's time, not in real time. So the reason why that might be useful is if you wanted to, say, implement something like UART, right, where a baud rate is expressed in terms of bits per second, this gives you a way to express that. There's also a simulated clock rate, which is 1 megahertz. For the SPI lab, I think you should probably only need to use delay cycles, though. Now, an important thing to note, though, is that when you call this delay cycles, that's the only time the simulated peripheral runs. So basically, either your code is running or the simulation is running, not both at once. Which, again, that's kind of a little bit unrealistic in that it basically means that all of your code happens basically instantaneously as far as the simulation cares, except for where you call delays, right? So that's why I said it was a little bit easier in that kind of with doing an SPI, bit-banged implementation on ADR, if you get a bit, you've got basically 4 cycles to process that before you have to process the next bit, assuming that you're running at 16 megahertz on the ADR and 4 megahertz on the SPI bus. Whereas kind of here, you can use as many cycles as you want to process each bit because, the simulation essentially is stopped. That said, though, I think it's a pretty good facsimile. You can also look at the C++ file that implements this if you want to. It's not really super exciting, so I'm not gonna harp on that. So now we're going to main.cpp. This is where your code lives. Now you might notice these are C++ files, and they do get compiled with G++. That's because Verilator is built around C++, not around C. So all of my example code and everything I've written and everything in support.cpp is really all just written like C code, not like C++ code. But if, I know a lot of you will probably have taken like 240 and you probably know C++, so if you want to use some C++ constructs, like if you're more comfortable with cout than printf or something, then go for it. But I would encourage you to kind of stick more to the C stuff, because this is kind of intended to be a C course in the embedded space that's still very C heavy. So, but remember, any valid C is also valid C++. So the fact that it is compiled with a C++ compiler doesn't matter. So I give you one constant here, which is the SPI clock ratio, and that's how basically the difference between the clock rate of the quote-unquote in a processor, which is really the simulations clock, and the SPI bus. So in this case, the SPI bus runs 16 times slower than the simulation clock. I think you could probably crank this down. I think if you got it less than somewhere around 2 or 4, I think that the SPI endpoint we're using would get confused. But I think just do keep it at 16, because that will keep it consistent across everybody and make it easier for us to grade. You've also got this one thing here where it says initialize simulation, and it gives you a simulation state. You don't need to worry too much about what's going on in here, but this basically sets all the Verilator stuff up. So you need this or the simulation won't work. And the simulation state basically stores the information that all of the utility functions that you're given need in order to operate. So let's go ahead and let's write a little bit of code. Also, remember, you should change your name up here. I've put my name. Your name is probably something other than what mine is, so don't forget to put your name on it. I got a lot of Lab 1 submissions that didn't have any names in them, which I didn't dock any points on that, but still good practice to say who wrote the file. So all right, so let's go ahead and write some code, and let's just actually, before we do that, let's just see what happens when we do a make clean to clean everything, and I'm going to say make waves. And so that's going to compile a bunch of stuff, and then it'll run our simulation, and then it'll open up a GTK waves window. And you can zoom out here, and you can see we've kind of got the clock going along, and then we reset kind of the peripheral device that we're simulating, and then we've got our chip select, S-clock, MOSI, and MISO. And you can drag this, you can click, and it'll move this little red marker around, and you can see the value of every signal at that point. And you can use just control and the scroll wheel to zoom in and out, like that. So these are really all the signals you need to care about for the purposes of this lab, but maybe if you know Verilog and you want to maybe kind of drill down into what's happening, you can actually expand this out, and you could go in here inside of say, this sensor module, and you could drop all these in here, and if you know how to, you can read them. But I'm not going to really cover that, because you kind of have to know Verilog, and it's also a little unrealistic, right? In the real world, you'd really just kind of have these top couple of things for the SPI bus. Okay, cool. So that's how we open that up, and I can also type make decode, and that'll run it through SIGROC. Which, of course, right now, nothing was transmitted and nothing was received. So that's not really printing anything out. This, by the way, this kind of SIGROC is how we're going to evaluate whether or not your code works or not. So you really want to make sure that this prints out what you think it should. We're probably not going to look at the GTK waves stuff so much for grading purposes. That's really more for you to be able to debug what's going on in your code. So that's more for you. Decode will not be as useful because it doesn't necessarily show you the timing of when each event happened, but it's a good way to kind of get validation that your stuff is working as it should. Cool. Okay. So that's how we compile. So now let's do something. So for example, let's just take MISO and let's drive S-clock, right? That's a good example. So I'll do that. So let's say we're going to just do for int I equals 0, I less than 10 I plus plus. So we're going to drive S clock for 10 cycles. So now what I'm going to do is I'm going to say write IO, and then S, which is the simulation state. And then we need to know which IO we're writing, so we're going to say IO SCK. And if you want to know what IOs are available, that's back here in support.h, where I say simulation IO. There's these 4, so this is where I'm getting that from. So we're going to do IO S clock, and then I'm going to write it high. And then let's drive it at 1/4 of the outer clock rate. So I'll say delay cycles S, and then we'll delay for 4 cycles. So that means that we're basically going to hold S clock high for 4 cycles. And then now we also want to pull it low, so we get the low part of that clock cycle. And I can say write IO S, IO SCK 0. And then I'll do delay cycles S 4 again. And there we go. And so now what we should see is the S clock signal kind of going up and down as a clock, a little bit slower than the main simulation clock for 10 cycles, basically. So if I make waves again, then it will ruminate on it. Oop, and it looks like we had an error. I forgot a semicolon. Well, that'll do it. I'm going to fix that. We'll try this again. Very good. And so now if we zoom out a little bit, there is our S clock. And so we see it's kind of going up and down and all that. Very good. You might notice there's kind of we told it to start kind of immediately, and there's kind of this big gap where kind of nothing's happening. The reason being that the peripheral device we're simulating requires a certain number of cycles before it's ready to accept input. So the initialization function will actually delay for a good number of cycles before it turns over control to your code. So that's normal. So this is where your code actually started running, or our code in this case, since I'm the one that just wrote it. But yeah, so we can see it going up and down, and there we go. And so that's how we would drive an I/O signal. And now this does have some stuff to help you, like if you accidentally do something, like if I try to say read IO SCK, it knows what direction everything goes in. So if you say make waves, it's actually going to crash out here. Oh, well, I guess it did crash, and then GTK wave still opened anyway, but you'll actually see it still was using the old version of the trace.bcd. It actually would have said error, SCK is not readable, direction is write only. And so it still was able to run GTK waves anyway because trace.bcd still existed from the last time we ran it. So you maybe want to keep an eye out for that and make sure that you're really looking at the waves that are most up to date for you, and not that it hasn't errored out and you're using an old version of waves. If you're not sure, if you type make clean and then type make waves, then apparently it will still do something. I see what's happened here. Yeah, so it's generated basically the waves up to the point where your code started running, because since your code crashed partway through, you still have everything that happened in the simulation up to that point. Actually, that's probably useful, because then maybe this would help you debug your code, because maybe if there was some kind of state that was on this bus that was getting it into causing problems in your code, you kind of still have that to see. I forgot that it worked that way. Okay, so in any case, so that's kind of how you would kind of run your code. So of course I'm not going to do the whole project, but this is kind of the gist of it. We could do a read IO if we picked MISO, which is the only input, master in slave out, right? So we're the master. So if I take make clean, make simulation, helps if you spell simulation right, then we can run the simulation and it won't error out, right? So if I take make waves, then I look here, kind of there was no error message or anything, because you are completely allowed to read MISO, since that's how you'll look at whatever the slave is sending back to you. Cool, neato. So that's how you do that. I think that covers pretty much all the functions that we have here. Don't call reset or initialize simulation again. Reset will send a reset pulse and reset the peripheral, which you shouldn't need to do. And initialize simulation will initialize a new simulation, which you also don't want to do while you're running. But yes, like I say, don't mess with these constants in here or anything, because when we go to grade your code, we're going to put in kind of the reference version of this. So if you've changed something in here, then your code may not run when we go to grading. All right, so that's basically how to use kind of this new setup in a nutshell. I think that's everything I had to cover for this video. So good luck, everybody. So I will look forward to seeing your projects.